everybody. Let's discuss how we can use the Lennard-Jones potential to predict the behavior of particles. Remember that the Lennard-Jones potential tells us the potential energy between two particles depending on how far apart they are. Let's suppose that we have two particles in the Lennard-Jones potential. The closest that they ever get to each other is 1.05 sigma. We want to know what the graph of their kinetic energy looks like. We've actually already done a problem much like this before. Remember when we did the example of the ball falling from a hand to the floor? We did this by determining the total amount of energy in the system and then ensuring that the total remained constant as the potential decreased. We can do a similar approach here. Let's start by asking ourselves, what does it mean that the closest that the particles can reach is 1.05 sigma? Well, think of the weight on a spring. What happens when the weight reaches its highest point? It comes to a stop so that it can turn around and start going down. If it didn't come to a stop, it would go farther than its highest point, which of course doesn't make any sense. It's the same thing with these particles. When the particles reach the minimum distance apart, they momentarily stop moving before turning around and separating again. Let's mark the closest distance on this graph. It turns out we now have all the information that we need in order to find total energy. We know what the kinetic energy is at this closest distance. It's just 0. And we also know what the potential energy at this distance is. The Lennard-Jones potential tells us that at this distance, the potential energy between the particles is right here, roughly negative 0.8 epsilon. So we know the potential energy and kinetic energy at this point, so we also know the total energy. It's just the two added up. But of course, because the kinetic energy is 0, the total energy is just equal to the potential energy. Let's draw in a dotted line to represent the total energy. Now we want to know what the kinetic energy looks like. I'm going to erase this little marker here because it's going to get in our way. Let's start with a location that we know. We know what the kinetic energy is at this point. It's just 0 because that's the closest the particles can approach. The kinetic energy graph cannot go to the left of this point because the particles are not allowed to get any closer than this. So what does the kinetic energy graph to the right of this point look like? Well, we know that the kinetic energy plus the potential energy always has to equal the total energy, which is a constant. So that means that if the potential energy is moving down as we go to the right, the kinetic energy must be moving up in order for those two things to cancel out. Once the potential energy levels out, the kinetic energy must level out too. And when the potential energy starts going back up, the kinetic energy must start going back down. But why do we end the kinetic energy graph here? Well, notice what happens at that point. At this point, the total energy and the potential energy are again equal. To the right of this point, the potential energy is greater than the total energy. This means that in order for the particles to be farther to the right, the kinetic energy would have to be negative. But we know that's not possible. Kinetic energy is always positive. So the particles are not allowed to go any farther to the right than this. So the kinetic energy graph must reflect that. This small region is the only region where the particles are allowed to exist. Particles like this are known as bound particles because they're not allowed to separate. They're stuck in this little well, bouncing back and forth. They have a minimum distance they're allowed to be apart here, and a maximum distance they're allowed to be apart here. In order to separate them, we would have to add extra energy. Let's do a second example that's slightly different. Now let's suppose that the minimum distance that the particles can have between them is 0.98 sigma. On the graph, that's about here. As before, we know what the kinetic energy of the particles is at this point. It's just 0 because the particles are at their minimum distance. So we therefore know what the total energy is in this system. It's just equal to the potential energy of the particles at 0.98 sigma. As before, let's start with the location that we know. We know that the particles have 0 kinetic energy at their point of closest approach, which is 0.98 sigma. So let's mark that on our graph. Now we need to complete the kinetic energy graph. We do this the exact same way that we did before. The kinetic energy plus the potential energy just has to equal the total energy. Since we know what the total energy is at every point, and we know what the potential energy is at every point, we just have to draw a kinetic energy graph such that when we add it to the potential energy, it gives us this line. I'm going to draw it, and then we'll discuss some of its important features. As before, when the potential energy goes down, the kinetic energy has to go up. However, notice an interesting feature about this graph that is different from the first one. The particles no longer have a maximum distance that they can be apart. Notice what happens to the potential energy as the distance between the particles gets very large. It gets extremely close to 0. However, our total energy is above 0 always. So if potential energy is 0 and total energy is above 0, then kinetic energy must also be above 0 as the particles get very far apart. The rest of the shape of the kinetic energy graph is basically just a mirror image of the potential energy graph. Remember that the kinetic energy plus the potential energy always must equal the total energy. These particles are unbound. This just means that there's no maximum distance that the particles are allowed to be apart. They're not actually connected by a bond, and they're just able to fly apart as far as they want. However, note that there is still a minimum distance. This is because as the particles get very close, the potential energy gets very big very fast. So it's very, very difficult to push the particles into each other, although I should note, not entirely impossible. I've left the Lennard-Jones potential up just for illustrative purposes. This is the equation in your DL manual for bond energy for a large number of particles. What does this symbol mean here? This is the summation symbol, and we're summing over pairs. What this means is that if we want to determine the bond energy of a substance, we just look at every single pair of atoms, calculate the potential energy between those two atoms, and then add all of those values up. This is fine, but there's one key problem. Let's imagine that we have a substance with Avogadro's number of atoms. Avogadro's number is a huge, huge number. Summing over all pairs would seem to imply that for each atom in the substance, we have Avogadro's number of other atoms that we have to calculate the potential energy for. What's more, each of these pairs are a different distance apart, and so they're going to have a different amount of potential energy. But it turns out there's something we can do to make this much simpler. In a previous activity, we saw that each atom has roughly 12 nearest neighbors. These nearest neighbors are sitting at the equilibrium distance, in other words, right at the bottom of this well. The next nearest neighbors sit at roughly twice that distance away, which is about here. Notice the potential energy of the next nearest neighbors is much, much less than the potential energy of the nearest neighbors. If you go even farther apart, the potential energy between atoms becomes almost 0. So it's a pretty good approximation to just take the nearest neighbor pairs into account when determining the total bond energy. Let's go back to our example with Avogadro's number of atoms. If each atom has 12 nearest neighbor pairs, and there is Avogadro's number of atoms, how many pairs are there in total? Well, your first guess might be this. We have Avogadro's number of atoms and 12 pairs per atom, so there's just 12 times Avogadro's number of pairs. However, this is not quite right, and let me show you why. Let's consider a much simpler configuration. Here we just have 3 atoms arranged in a triangle. If you count, each atom has 2 nearest neighbors. And there are 3 atoms. So if we multiply the number of nearest neighbors by the number of atoms, we get 6. However, there is clearly not 6 bonds here. There's only 3 of them. So taking the number of nearest neighbors and multiplying by the number of atoms actually double counts the number of bonds. So we have to divide this by a factor of 2. So for Avogadro's number of atoms that are tightly packed, we expect there to be 6 times Avogadro's number nearest neighbor bonds. But remember, this is not quite what we want. We want to know what the total bond energy is of the substance. This equation says that the bond energy is just the sum of the potential energy between all the pairs. So all we need to do to get from a number of bonds to bond energy is multiply by the potential energy in each bond. The potential energy in each bond times the number of bonds is just equal to the total potential energy, which is the bond energy. How much energy is in each bond? Well, it's just negative epsilon. These bonds are nearest neighbor bonds, meaning the atoms or molecules are sitting at the equilibrium distance and have negative epsilon of potential energy. So there's our answer. The bond energy for Avogadro's number of particles packed together tightly is negative 6 times Avogadro's number times the well depth for the particles. Of course, we don't have to do this for Avogadro's number of particles. As long as the number of particles is fairly large, this approximation always works. You just have to replace Avogadro's number with the number of particles in your sample.